right, it's a good time. So let's get the lecture started. Hello everyone. Can everybody hear me well? Can you guys see the presentation slides? Good. Thanks all for coming to the lecture. This is the CS292F. Today we're going to be doing the first lecture on the algorithms for the more general family of convex optimization algorithms that focuses on non-smooth optimization. So I hope everybody has been enjoying doing the homework one. So I want to emphasize that the homework is a big component of the structure of this convex optimization class. It's arguably the only the only evaluation and the only part where you get to actively work out things yourself. And that is, in my opinion, the most important components of learning. So unless you know how to do the homeworks, unless you complete the homeworks yourself, so sitting through the lectures, it's only gonna give you a superficial kind of understanding of the materials. It will only give you a fake sense of belief that you have understood the materials well. So it is only after you've done your homework when those materials has become truly yours. So I cannot stress the importance of homework more. So if you are finding yourself struggling through the homework, and then at the end of the day, you found yourself learned more from the homework than you have learned from the lectures, and that's the intended that's the intended effect of the design of these homeworks. So so don't be don't be intimidated by the homeworks, since it's a big part of the evaluation. So you are supposed to spend time to do it, and that really helps you to understand the materials better. And I hope they also will help you to appreciate the content of the lectures better in subsequent parts of the class. Okay. Now that we're seeing more participants, so let's start the lecture. So last time, actually the lecture before last time, in lecture 4, we talked about gradient descent, which solves the following problem, convex optimization problem, that we want to minimize f of x when x is unconstrained. So so in this case, we assume f is convex and differentiable, and the gradient descent algorithm simply starts from any initialization and move towards the gradient direction by a little bit in every iteration. And then as you keep repeating this recursive call of gradient updates, as k gets larger, the case iterate of your parameters will converge to somewhere near the optimal solution. Okay, we talked about the step sizes. The step sizes tk can be chosen to be fixed as a function of properties of this function f that we're minimizing, or we can alternatively choose it adaptively using backtracking line search. In particular, if we make the additional assumption that this f is not only convex but also gradient Lipschitz or strongly smooth, then we know that we have shown that the gradient descent have a convergence rate of 1 over k, or have an iteration complexity of 1 over epsilon of getting to epsilon suboptimality bound. The drawback of gradient descents, on the other hand, is that we require this function to be minimized, f to be differentiable. And also it can be so that motivates today's lecture when we talk about the subgradient methods. Okay. Now another part of today's lecture is going to be about proximal gradient descent, which tries to address the problems that subgradient methods are often like too slow in convergence. So we'll see the computational guarantees of the subgradient based method, and that's the part of the purpose of learning subgradient in the previous lecture, where we had to go through detailed mathematics about subgradient. So you now have the necessary theoretical underpinning of what the subgradients are, and now we can make use of it to start constructing algorithms. Okay, so just a quick recap of the last lecture. We introduced the concept of subgradient and subdifferential. So we use this partial f notation to denote a set of all subgradients at the location, say x. And any individual element of this set of subgradients, any individual element of the subdifferential satisfies this condition, which resembles the first order definition of convexity. Okay, so notice that so I'm adding this x here. So notice that this holds for all and x and y. So if you replace a subdifferential with a gradient, then it becomes the first order definition of convexity for differentiable functions. Okay, so subdifferential and subgradient can be thought of as a generalization and of the family of differentiable functions that allows us to talk about non-differentiable convex functions. Arguably, that's the very interesting part of convex optimization problems, in which case you can deal with non-smooth functions, and it happens that those non-smooth functions have interesting properties that allows us to design and use it as a language to design structures that the optimal solutions would satisfy. So we'll see more of that in the examples of today's lecture. Then we talked about the subdifferential calculus, where we learned how to evaluate and calculate the subgradients for functions that are the sum of two functions, and functions that are a composition of a convex function and an affine transformation, and also functions that are slightly less trivial, functions that are pointwise maximum and pointwise supremum of other convex functions, where as long as we can evaluate the subgradients of the individual components, we can use it to construct the subgradients of this more complicated composite function. And perhaps of the most importance about subgradient is that it gives us a very concise characterization of optimality, even and this holds even beyond convex optimization. So for any function f, if it admits a minimum, an argmin, if this argmin is not an empty set, then parameter x is the optimal solution to the problem that minimizes f of x, is equivalent to 0 is a part of the subdifferential. Okay, so this generalizes the standard first order optimality conditions that you might have learned since high school, that the gradient needs to be 0 for convex differentiable function. It's a generalization. Okay, so now that we've learned this this canon or this hammer, so in today's lecture, let's apply subgradient and design algorithms so that we can solve a much larger family of problems than that could be solved using simply the gradient methods. Okay, so today we're going to be talking about subgradient methods and proximal gradient methods, and then we'll give examples about this iterative self-thresholding, algorithm, and its applications to matrix completion. And towards the very end, we'll be talking about acceleration. And in between, when talking about the algorithms, as usual, we'll be providing insight of how these algorithms are constructed and how we can analyze these convergence properties so that we can say state computational guarantees that are consistent with our computer science understanding of algorithms. All right, so let's get the actual lecture started. So Instead of considering f being convex and smooth, so let's consider a family of functions that are only convex. Okay, so notice that this is something that's significantly more general, that can even cover things like indicators, and it can be used to take care of piecewise linear and piecewise quadratic functions and so on and so forth. Okay, so the subgradient method is very easy to state. So much like a gradient descent, so you're moving towards a negative gradient direction. So in subgradient method, you can also just start with any initialization and move towards the direction of any subgradient at your current iterate. Okay, so provided that you choose the step sizes appropriately, and this algorithm is always going to get you down slope, and you'll always be able to minimize the objective function as k goes to infinity. Okay, simple, right? So this is exactly the same as a gradient descent, except that you replace the gradient with subgradient. Okay, so notice that this can be any subgradient in the subdifferential. So it doesn't matter like which one you pick, as long as you can construct one. So that will be good enough for the interest of implementing the subgradient method. Okay, this is useful because as we've seen in the last lecture, finding one component within the subdifferential is easy, and often characterizing the set of subdifferential is not that easy. It's often actually quite technical. So this is a good news, because it says in practice, as long as we can just construct one subgradient at any given location xk minus 1, then we can use it to construct an iterative algorithm that happens to work. Okay, there's one little catch. Instead of just like in gradient descent, if for people who still remember the analysis, the first thing that we talk about is something called a descent lemma, which says that if you follow the gradient direction with sufficiently small step sizes, and the function is convex and gradient Lipschitz, the function is gradient Lipschitz, you don't actually need convexity. Then you are constructing a monotonically decreasing sequences in the objective function value corresponding to each iterate. That property is not true for subgradient method. So therefore, instead of comparing to the current iterate, instead of providing a theoretical guarantee for the current iterate xk, so the convergence guarantee is stated for the best iterates that you have run into so far. Okay, so this is easy to do if you can evaluate the function. So you basically keep track of all the function evaluations throughout your optimization, and then keep track of the minimum. And if you happen to run into a better better solution, then you just cache that, right? You just save that on the side, and then you can without spending any additional memory, and you can at the end of the day of the optimization, you can just output the best iterates throughout the training. Okay, so there's a question on the group chat. Is there any reason why we keep track of all previous values rather than just keep track of the previous value, which is guaranteed to be minimum? Well, I'm not sure if I understand the question correctly, but you don't have to keep track of all previous values. You only have to keep track of the minimum of all previous values. That's like the order 1, like memory footprint, rather than the order k. Additional memory. Okay. Okay. So just like gradient descent, we'll have to talk about how do we choose the step sizes appropriately. Okay. So there are often two like standard choices. So we can either take the take the step sizes to be fixed. In which case, if you allow k to go to infinity, this will not really converge, as we'll see in the theorem on the next slide. But suppose you know a priori, like what is the number of iterations that you're willing to run, what is the available computational resources that you have, then you can potentially set this tk as a function of the total number of iterations that you want to run as a fixed value. So that would work just as well as using diminishing step size. On the other hand, like diminishing step sizes allows you to solve the problem when you do not know how many iterations you should want to run a priori. Okay, so that is the reason why like this a sequence of step sizes that goes to 0 that satisfy these two conditions are step sizes that that goes to 0, but you don't have to specify what k is, and eventually you're in some sense doing something similar to simulated annealing, and then you move a smaller and smaller step in every iteration, and until the end, you can imagine that this will always lead to something that converges. Okay, so the specific requirement for the choice of diminishing step sizes are that they are square summable but not summable. Can anyone come up with a sequence of step sizes that satisfy this property? So the easiest way to answer this is to just type into the group chat and I will announce your answer, or you can unmute yourself and then just state your answer. 1 over square root of k. So okay, so that's an excellent answer. Let's check whether this whether this choice of step sizes actually works. Okay, so suppose you choose tk to be 1 over square root of k. Okay, let's check the second condition first, right? So you get 1 plus 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of k. Okay, so let's try to provide an upper and lower bounds of this. So first of all, maybe a lower bound. So since this is diminishing, then we can lower bound this by k times square root of k. Okay, so this is equal to square root of k. Therefore, it goes to 0 as k gets larger. So it definitely checks the second condition. Okay. So is square root of k the right order? Well, we can also see that by simply we can also see that by providing an upper bound of of this. So it turns out that by just upper bounding this quantity and then take only the a portion of it and then double it so that it covers everything ahead, then you can show that the order of the summation is also on the order of square root of k. Okay, so it checks this condition. However, let's check for the first one, right? For the first condition, you have 1 plus 1 over 2 plus 1 over 3 plus 1 over k, right? Is this something that sum up to a finite number if you take the limit of k goes to infinity? So anyone can answer this? Yeah, this is I guess a little bit less straightforward. So it's unclear whether this is something that's gonna that's gonna converge. But the one way to think about this is to do the integral to instead of solving a summation, you solve an integral of 1 over x dx. So you can clearly see that this integral by using simple calculus that this is not really bounded. In fact, this is what we call a harmonic sequence, and it can be shown that without taking this k to be infinity, this is proportional to order log k. Okay, therefore, like it actually goes to infinity at a very relatively slow rate. Okay, so the choice of learning rate with tk equals to 1 over square root of k is something that that doesn't actually satisfy the first condition. You need to go a little bit, you need to converge to 0 and diminishing a little bit faster than this in order to satisfy the first condition. Okay, so I guess the choice of this learning rate tk can be chosen to be can be chosen to be 1 over k to the power of beta, for beta chosen to be larger than half, but smaller or equal to 1. Okay, so that will be the reasonable scheme for parameter. So after we've done the analysis, we'll see like what is the best choice of a fixed or sequence of diminishing step sizes to use for subgradient methods. Okay, yeah. So so comparing to gradient descent, the key difference is that we don't actually have access to we don't actually have access to an easy way to adaptively choose these step sizes like backtracking line search. Instead, you have to plan ahead of time to design a sequence of step sizes and choose this carefully so that you guarantee the convergence of the algorithm. Okay, so there's a question said, what if p is larger than 1.2? By p, do you mean beta? Yeah, I assume that you mean beta. So you can choose any beta that with beta larger than half, but also smaller and smaller.
Before you write the beta equation. Sorry about that.
Okay, so so in order to prove convergence, there's one additional assumption that we'd like to make so because general convex functions can be arbitrarily pathological. You can have points that changes extremely quickly. Then sometimes local descent-based methods or subgradient methods will not really work effectively there. So in this case, often like without loss of generality. So besides functions such as indicator functions, most convex functions are actually satisfying this condition called Lipschitz condition. Notice that this is not a gradient Lipschitz condition, but rather just a Lipschitz condition of the function itself. And by its definition, it's saying that when we adjust the parameter by a little bit, then the function value also changes by something that's at most proportional to the changes of your parameter. Okay, and you need this to hold for all pairs of input. For instance, take this absolute value function. Can anyone come up with the Lipschitz the Lipschitz constant of this function? Yes, excellent. There's an answer. So basically, if you take any 2 points, x, y, and then the slope of this is actually g. So you can think about this g as a supremum upper bound of the uniform upper bound of the magnitude of the gradient. Okay, so you can take g to be for differentiable functions. You can take this to be okay. And for I guess for non-differentiable function like this one, so if it suffices to take the essential supremum of this function, which says that you take the maximum of this besides a measure 0 set where on which this function is not really differentiable, which applies to the absolute value. Okay, so let's look at the two theorems on the convergence. Suppose we choose the learning rate t to be a fixed step size, then it can be shown that the case goes to infinity. You converge to something that's that's suboptimal with a parameter that's proportional to t. Okay, so suppose we choose t. Suppose we want to run this for k iterations. We can choose t to be say 1 over square root of k, and then hopefully with that many iterations alone, it's going to converge to this 1 over square root of k neighborhood. So we'll see how that works very shortly. Okay, and as k goes to infinity, if you choose the diminishing step size is satisfying the two conditions of quadratically summable but not summable condition, then as k goes to infinity, it can be shown that the best iterate like throughout the process of optimization actually converges to the global optimal solution. Okay, so let's see how it works. So basically, this follows a very similar structure to the telescoping sum, comparing to the strongly convex the convergence analysis of strongly convex function. But the choice of the learning rates needs to be chosen slightly different. So in some sense, we're canceling out the we're using telescoping sum of the adjacent iterate by comparing the argument's distance to that of the optimal solution. Okay, so let's prove that more formally in the on the written board. Okay. 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 So assumption is the G Lipschitz F, satisfying that Fx minus Fy is smaller than G X minus Y. And well, theorem Fx k best k goes to infinity is equal to F star. Okay, this is what we're trying to prove. So along the line, we'll also see the convergence rate. When we choose the parameter appropriately. But for now, let's state this theorem. When tk chosen to be sum of tk equals to infinity and sum of the tk square is finite. Okay, let's prove this. So we start by writing the distance of the current iterate with that of the optimal solution. Okay, and then the first thing that we do is to substitute the algorithm. So notice that the algorithm is xk xk is equal to xk minus 1 minus tk of subgradient at k minus 1. Okay, so that's our algorithm. So by substituting this algorithm into this equation, we get xk minus 1 minus tk gk minus 1 minus x star. All right, so let's like combine this term and that term for the interest of trying to construct the telescoping sum. Okay, so let's combine these two terms and then expand this quadratic function. So like before, we have the two square terms, tk square, gk minus 1 square, and then there's this cross terms that we cannot miss. So this will be minus 2 tk, and then we have a inner product of gk minus 1 transpose with xk minus 1 minus x star. Okay. So there's only like one additional, I guess two additional conditions that we didn't apply. So one is this G Lipschitz condition, and the other is a convexity of a function f, right? So and the fact that the gk minus 1 is a subgradient. So by convexity of the function f and the fact that G is a subgradient, we know that for any we know that f xk minus 1 is larger than it's larger than fxk minus 1 plus gk minus 1 transpose x star minus xk minus 1. Right? So this is simply substituting the any choice of xy pairs and substituting into this definition of subgradient, with specific choices being y equals to x star and x equals to the k minus first iterate. Okay, so with that, we actually have constructed we have actually constructed an upper bound of this quantity. Okay, so let's see why is this upper bound. So if we change this, so let's maybe write it out. Minus 1 minus x star square plus tk square gk minus 1 square. Let's make it plus 2tk gk minus 1 transpose x star minus xk minus 1. Okay, now this is the same as this term. So if we move this to the other side, then that gives us an upper bound. So we can write we can write this as xk minus 1 minus x star square plus tk square gk minus 1 square and plus 2tk, and what we have f f star minus fxk minus 1. All right. So so with that, it remains for us to it remains for us to apply like the G Lipschitz condition, right? So since we have G Lipschitz condition, we know that all the subgradients are actually satisfying that the subgradient has a 2 norm that is smaller than G. Okay, so that says that we can further bound this with tk square G square plus 2tk f star minus fxk minus 1. Okay, so notice that f star is always smaller than fk minus 1. So let's make this let's make this minus. Okay, so now we have a nicely looking telescoping structure with this and that on two sides of this inequality. Okay. So by telescoping for k steps, we get, yeah, basically take a k to be from 2 to say k, and then just add everything up and canceling everything that's that's in between. Then we get minus x star. So this is the only thing that's left, being smaller than x, I guess x1 minus x star. Okay, so these are the only thing that remains. Let's make it x0 so that over here we are summing from L from 1 to k, and TL square G square minus 2 sum of L TL F star minus F star plus F X L minus 1. Okay, so from this proof, then it is very clear that the choice of this and that becomes the choice of TK becomes important, because provided that the TL are square summable, then we know that this term is finite. And provided that the TL is not really summable, then it means that this will go to go to infinity as k gets larger. Okay, so if we move the last term to the other side, so let's flip into a new page. By moving the last term on the right hand side to the other side, we get 2 times the sum of TL, L from 1 to k, F, I guess L minus X L minus 1 minus F star. And on the right hand side, by moving the case iterate to the right hand side, we get x0 minus x star square minus xk minus x star. So notice that this is negative, so we can drop this term. And what remains is the additional sum of TL square from I from 1 to k. So let's see what else that we have. Okay. And G square. Okay. So let's start from the left-hand side of this inequality and lower bound this, since all the TIs are non-negative, so we can lower bound the left-hand side of this inequality with 2 times L equals to 1 to k TL. Let's group this together and then have f of x, I guess k best. Notice that this fxk best minus ff star is always smaller than any individual iterate. Therefore, we can construct this lower bound. But now that everything here about the step sizes are grouped together, we can divide both sides by this sum of step sizes. And finally, that gives us fxk best minus f star being smaller than square divided by 2 TL L from 1 to k plus divided by okay. Yeah, that provides the final bound, and if you substitute our condition on a diminishing TL, we complete okay. So is that clear to everyone? Yeah, so another thing that we can directly read off from this convergence proof is that suppose we only want to run for k iterations, for capital K iterations, and want to use a fixed learning rate t. Okay, what is the t that we can be we need to be choosing, right? So this actually simplifies the picture quite a bit, right? So let's say that let's say that we use b to denote the upper bound. Okay, so let's say that x0 your initialization is at most be away from the optimal solution. So suppose the solution set is bounded, then you always have a constant b here. So it may potentially depend on the dimension, but let's not worry about it right now. So the above bound can be simplified. Can be simplified for the fixed learning rate to be b square over k times t, right? And plus k times t square over k times t, g square. So this is half b square over kt plus t g square. So the optimal choice of t, is the one that makes these two equal, right? So we want to choose the b square kt plus is equal to tg square and move t to the other side, and we can show that the optimal choice of fixed t here is b over g divided by square root of k. And that means that when we choose this optimally, the final convergence rate, after running for k iterations with the best fixed learning rate is going to be order of bg divided by square root of k. Okay, and the corresponding iteration complexity. The corresponding iteration complexity would be order of 1 over say this is epsilon 1 over epsilon square. Okay, so when epsilon is 0.1, then it takes only 10 iterations for gradient descent to converge, but it will take 100 iterations for stochastic for subgradient descent to converge to a similar optimal solutions that are epsilon away from the actual optimal solution. Okay, let's take a step back and look at the two iterates. So the first one is something that we construct completely coming from applying the definition of subgradients. And once we have this structure, we can just iterate until the last iteration and telescoping the leading terms. And that allows us to construct the summation of the step sizes it takes a little bit of delicate choices of the step sizes, but once we have that, once this term goes to infinity, but this term goes to infinity, but this term do not go to infinity, then asymptotically those are valid learning rate choices that eventually leads to an algorithm that converges. Okay. Okay, so we've talked about this. We've talked about this. All right, so I'll give one example and then we'll go to our 5 minutes break. Okay, so let's consider the problem of regularized logistic regression. Okay, so wait. Okay, so let's go to our the regularized logistic regression. So the standard logistic regression have a loss function that's a summation form, and we're summing over the n data points that we have, and in each data point, we can write the logistic loss when y is chosen to be -1, 1 in this form. So there are various different form of logistic various different form of logistic loss. So when y is in -1, 1, so there's a different versions that might be more familiar to many of you. So that would be log of 1 plus exponential minus y, and then xi transpose beta, right? So that would be the corresponding logistic loss. And this is a version of the logistic loss when you convert this domain of y to 0, 1. So either of these are valid logistic loss. And how do these loss function look like? So logistic loss look like the following. So the horizontal axis is the score function. So the score function in this case is xi transpose beta, multiply with a true label. Okay, multiply with a true label, and if your score function is positive and the true label is 1, then you end up getting something that's close to 0 on this leg. And if your prediction have a different sign to y, then you suffer a large loss that shoots up linearly. So you can think about this as a convex surrogate of the 0, 1 loss that gives you a loss function of 1 when your prediction is wrong, and gives you a loss function of 0 when your prediction is correct. Okay, so I assume like many of you have seen binary classification problems in the context of either statistical learning or in your basic machine learning course. Okay, and this is also closely related to cross entropy, which is something that I encourage you to work out and figure out the exact details. So for the interest of this course, let's inspect this loss function f, and notice that this is a differentiable function everywhere, and by the shape of it, this is also a smooth function where the gradients are changing relatively slowly. So you can work this out by calculating the second derivative of this function. Okay, but what if what if we penalize this this loss function by an additional penalty, sometimes maybe of the form of 1 norm, in which case we would like to use it to induce additional structure, of sparsity. So we'd like to prefer those solutions that simultaneously minimize the loss, but also have small L1 norm. Maybe like if I do not want sparsity, but I just want to have a better bias variance trade-off, I can come up with other regularization term called ridge regression regularization that adds a like quadratic square 2 norm, which is the same of beta transpose beta. So that would make any problem strongly convex with a parameter 2 lambda. But suppose we have the L1 norm, then suddenly the objective function becomes non-differentiable, and we suddenly cannot use gradient descent. And notice that if we have a strongly convex problem like this one, and the convergence to its optimal solution takes only log 1 over epsilon iterations. On the other hand, like suppose you use subgradient methods for this problem, it takes an order of 1 over epsilon square. That's an exponentially worse computational guarantee if we just use the subgradient methods naively. Okay, so let's compare the two methods. So suppose we use gradient methods for the ridge regression. Then on the left-hand side, we can see that it converges linearly. So this is a semi-log plot where on the horizontal axis you have linear scale, and on the vertical axis you have log scale. Okay, so a straight line on these semi-log plots means that you have linear convergence. Okay, so the vertical axis is f minus f star, where f star is the value of the optimal solution. Okay, you can see that it converges linearly until you reach numerical precision that can be represented on finite computer. On the other hand, like suppose you use a subgradient method, then you can never really get anywhere near that ballpark of 10 to the power minus 13. So it takes significantly more iterations before you reach somewhere that's good. So the best solution during the iterate occurred here and is in the neighborhood of 0.01. Okay, so in practice, subgradient methods is significantly slower than the gradient-based method. And with that note, we'll take the break and we will resume at 2 o'clock. Meanwhile, if you guys have questions, like please write your questions in the group chat, and I'll respond to that during the break, and then maybe at the beginning of the second half of the lecture. There's a question about logistics. Alex asked that once everybody have turned in their homework, will we be releasing solutions to the homework? So this is a very good question. So like I said, the homework is a big part of the course, and of course for those questions that you did wrongly or didn't or wasn't sure what the right solution is, you should um, you should get the necessary feedback so that you can revisit those questions and then clarify your doubts. So unfortunately, we won't be able to release the solutions. Actually, we don't have the solution written out nicely on a piece of LaTeX file. On the other hand, we are providing feedback. So I'll be coordinating with my TA. So Kai-Chi will be making use of his weekly office hours and to answer questions related to those that he will poll on Piazza and ask for a subset of the questions that are trickier than others. We'll be providing a live discussion and providing the solutions online. Okay, so unfortunately, we won't be able to provide the solution files as a PDF for the interest of future offering of this course. There's a question on could you give one example that subgradient results in non-decreasing sequence, not at minimum point? What does it? Could you clarify your question a little bit? What does it mean? So the picture that's shown on this slide is one example where subgradient is not producing a monotonically decreasing sequence. You see it goes up and down as k gets larger, and it's not really monotonically decreasing. So yeah, so with yeah, so let me clarify that question a little bit further. So clearly it depends on the choice of the step sizes. When you choose the choice of the step size to be 1/k, right? So when you choose this, then on this particular example, you see that it actually decreases objective functions monotonically. But that is not really guaranteed for many functions that are more fundamentally like non-differentiable. So this particular function has like one point that is non-differentiable. So it behaves closer to gradient based methods. Which it shows that it is monotonically decreasing when t is chosen to be 1/k. But when you choose this t to be, say, closer to 1/square root of k, so maybe k to the power of 1/3, the picture might be different. And And it also depends on the problem. So what the non-monotonicity is saying that we do not have a guarantee that the moving towards the subgradient direction is actually going to decrease your objective function value. So so think about maybe like a piecewise linear function, right? A piecewise linear function that looks like these. Okay, so suppose this is a function of f of x. Suppose you're right here. You're only like a little bit away from this curvy point. Let's say you are here. Okay, so this is epsilon, and epsilon is smaller than it can be arbitrarily small, and the only information that you have here is a gradient direction. But notice that this gradient direction is pointing towards the right hand side, right? So that's the only subgradient here. And if you move towards the step size, and the current step size happen to be say 2 epsilon, then the next point will be right here. So without the gradient smoothness, without the additional assumption that the gradient changes slowly as you move along, so you won't be able to achieve anything like the descent lemma, like in the gradient descent. So moving from x1 to x2 towards the gradient direction will actually increase the objective function value. Okay, I hope that clarifies, and that maybe that was a question that you were asking. Okay, so so let's move on. So we talk about two different choices of learning rate. One, choosing TK to be fixed when we know the number of iterations to run a priori. And we also talk about the diminishing step sizes satisfying certain condition that guarantees convergence for any time algorithm without knowing how long you are going to be running that algorithm. So there are other choices of the algorithm of the step sizes that allows the algorithm to converge often with additional knowledge that's available. Like suppose you know what the optimal value is, then you can do a little bit better. You can choose something that's more appropriate. So specifically, the Polya step size is choose TK to be the value of your current iterate minus the optimal objective function value divided by the square of the size of the subgradient. Okay, so this bizarre looking choice of the learning rate, like it's definitely data adaptive because it only requires you to evaluate the objective function value and construct one particular subgradient. So it's clear when we look at the first step of the convergence proof, right? So notice that you have this TK here, you have the TK square here, right? So by choosing this TK to be this particular value, then that allows us to say on the second part, cancel out this GK minus 1. So when we substitute this into here, we get f of xk minus 1 minus f star, and over here we get the square of that. We get 2 times f xk minus 1 minus f star square divided by gk minus 1 square. Okay, so once we have these, then that allows us to construct the convergence like the same kind of telescoping while depending on the sequence of the sums of the gradients and the square of the objective function values in a more systematic way. So the thing is that with this special choices of the learning rate, hopefully more a cleverer choice of the learning rate, we're not actually going to improve the convergence rate significantly. So I leave this as a quiz questions to actually work with this learning rate and do the telescoping and then construct the final bound. But let me jump to the conclusion. Once we choose this learning rate appropriately, the final convergence rate is still like 1 over epsilon squared. So you may improve a little bit on the constant, But at the end of the day, you are still not doing too much better than that in the worst case when you choose a fixed sequence of learning rate. Okay, so there are like interesting cases where choosing the polyac learning rate is more meaningful. So let's give such an example. So suppose we want to solve this convex feasibility problem. So this is the first time this appears, feasibility problem, which means that we'd like to find a solution that that satisfy a set of constraints. Okay, so you have a convex set, C1 to Cm. All we want to find is to find a solution that satisfies this set of conditions. Okay, a constraint satisfaction problem. Okay, so for instance, you can think about Sudoku, right? Which the solution X needs to satisfy that the sum of all the rows and columns and all the little boxes in between needs to needs to be like 1, 2, 3, 4, 5, 6, 7, 8, 9. But a convex relaxation of that would say that the sum of it needs to sum to the same number rather than this combinatorial constraints. So that's actually one solution that you can use to solve Sudoku. So when these constraints are convex, you can change this problem into something that's slightly different, that depends on the distance to a convex set function that we defined in the last lecture. Okay, so again, the distance is equal to the Euclidean distance of x minus projection of x to this particular location, to this particular set. Okay, and then we can solve this feasibility problem by solving an unconstrained minimization problem with this reformulation. So instead of solving the feasibility problem directly, we can solve the minimization problem that's constructed by the maximum of the distance to convex set. Clearly, if we know that there's one solution that exists, then the optimal solution of this would be 0. So that would be like one instance where we know what the optimal solution is even before solving the problem. Okay. So let's apply the polyac learning learning rate to this problem and see what is the algorithm that we get. We've already worked out that when x is outside the convex region C, then the distance to convex function is actually a differentiable function from the previous lecture, and the gradient is this, right? So it's a difference between x and the projection of x, and then you normalize it according to the distance. So this makes intuitive sense because, say, projection to the line segment will have a distance to convex set conditions that looks like that. What this is saying is that if you are right here, then your gradient is just the distance from this to here divided by the magnitude. So you are getting the unit vector that's pointing towards the convex set in the middle. Okay. Recall the subgradient rule. So we learned about this in the last lecture, that the subdifferential is a convex Hall of all the subgradients of each leg of this function in this pointwise maximization over all the functions that are active at this location x. In other words, it is relatively easy for us to construct the subgradient. Okay, so the subgradient, it suffices that we find like one particular function that is active here by actually evaluating argmax, right? By finding argmax f of then fjx, and you take the gradient of that. would give us one particular subgradient in the subdifferential. Okay, so so let's do that. Suppose we put these two facts together and then construct the subgradient this way, and then using the Polyak step sizes, and this will be the subgradient update rule that we come up with, right? So we're moving towards the subgradient direction. So again, this is a subgradient, where this CI, so these are chosen to be the arcmax, right? So it's the arcmax, it's the CI that's farthest away from xk minus 1 that ensures that xk minus 1, if xk minus 1 is not yet feasible, then this is a region where the distance function is actually differentiable. So we can construct the gradient, and that becomes the subgradient of the actual function. So the Polyak step sizes, when you specialize this to this special case, it simply becomes it simply becomes fxk minus 1. So let's go back to Polyak step sizes and look at what it actually is. Okay, so notice that this is what it is, and then in this case we know that the gradient is always a unit vector. That's why all we get is this fxk minus 1 minus f star divided by something that's a unit vector. We substitute this here at the learning rate, and well, what is fxk minus 1? So by definition, it is the distance of fk minus 1 to the farthest convex set in C1 to Cm. But that's exactly the same as a denominator. So these two actually got canceled out. So once we have that, these two are also canceled out. So all we are left with is the projection of xk minus 1 to this farthest to this convex sets that are farthest away from their parent iterate. So that gives us this very interesting algorithm that actually solves the feasibility problems by the so-called alternating projection. So take two sets. So this involves just alternatingly project your any given initialization to one set, and then to another, and then to another, then to the other set, until you end up finding a solution that's feasible. Okay, for more than two sets, this involves like finding the set that are farthest away and then start minimizing that maximum. Okay, but this is a very intuitive algorithm. Even if you do not know what subgradient descent is, this should be an intuitive algorithm that you might be able to come up with. And it's not intuitive at all. Why this naturally corresponds to a particular gradient descent or subgradient style algorithm with a carefully chosen learning rate. So this is what happens. So people come up with all sort of algorithm to solve optimization problems, but often towards the end of the day, it's noticed that many of those algorithms are secretly gradient-based methods. They are secretly gradient descent or subgradient descents with specific choices of learning rate. Example of these include not just this alternating projection for finding a feasible solution to the intersection of convex set, but also things like non-negative matrix factorization, and things like what we've seen before, like eta boost. So by the time this algorithm were put together, like people do not know that they are actually gradient first order methods. But at the end of the day, like there's this nicely looking gradient methods based interpretations that allows us to understand this better and then adapt this to other problems with other special structures that you can simply modify by changing the objective function value. Okay. So there's an extension of the subgradient methods that allows us to deal with the constraint as a convex set quite a bit better than using the subgradient methods directly. So first of all, notice that if we write f of x to be something like a gx plus indicator c of x, then this is not really a function that satisfies the G Lipschitz condition. Why is that? Answer is no. So the reason is that this indicator will give you infinity the moment that you're outside this convex region C. And when you are inside, you are 0. So this is actually not the Lipschitz function at all. So the standard subgradient method doesn't really apply here. However, like when you are solving this problem, there's an alternative algorithm called projected subgradient method that moves along the a particular subgradient direction, negative subgradient direction, and then project it back to the convex set. So this happens to work. Okay, so so the reason why it works is the following. So xk minus x. So let's try to understand this a little bit. So this is equal to x k minus 1 minus tk gk minus 1, but then with this projection operator here, minus x star. Okay, so this is what we have from this projected subgradient method. But what we want is that if we can construct an upper bound of these by showing that we can drop this projection operator, then we can just follow everything that we have seen before and then prove the convergence as if this is the unconstrained problem. The question is why is this inequality true? So to see this, notice that the projection C of x star is the same of projections. It's simply x star, right? So using the fact that the projection operator is a non-expansion, this gives us exactly this inequality. Okay, so so intuitively, this is saying that when you project any points to a convex set, then it is only moving it closer to any of the other sets that's within the set. So that should be intuitively true. But I leave it to you to read up on non-expansion. We'll also see this again when we talk about online convex optimization. Okay, so so while this is a useful algorithm to have, often projection to a given convex set is the non-trivial thing to solve in the first place. Specifically, there are things that are easier to project to, like affine images, like solution set, like some kind of norm balls, non-negativity cone. So these are examples of convex sets that are relatively easy to project to. So even like by easy, I mean have a polynomial, easy polynomial time algorithm to solve. Like for this one, those are really easy. For these ones, not so much, not so easy. It sometimes involves solving a linear system which takes a polynomial time proportional to say n square or n cube of how large this matrix A is. And often the projection step itself involves solving a convex optimization on its own. So even though projected gradient descent works, it doesn't really like projected subgradient method works. Like the current analysis from the subgradient methods doesn't really illustrate the benefit of doing that too significantly. Okay. So we'll revisit this once we talk about the proximal gradient methods. So so one question that we'll keep asking ourselves in this course, once we have a computational analysis of an algorithm, is that whether this is the best that we can do for the family of problems that we're trying to solve. It turns out that for subgradient methods, it's actually more or less optimal. So so Nesterov in one of his seminal constructions showed that for the Krylov space methods, among all the Krylov space methods that operates within the span of the sequence of subgradients that are produced by the algorithm, if you're only willing to assume that the function is Lipschitz, then there are such functions that are Lipschitz but not but not smooth, such that you actually need, like for any such method that are like non-smooth first order methods that require this many iterations to converge. So the convergence rate is on the order of 1 over square root of k, which translates into iteration complexity of 1 over epsilon squared. So in that sense, the subgradient method is indeed the best that we can do for this family of methods. So that sounds pretty pessimistic. What if we are adding additional assumptions? So we talked about adding strong convexity to the problem of gradient descent. For gradient descent, if we add strong convexity assumption to the function that we're minimizing, we can improve the convergence exponentially from 1 over epsilon to log 1 over epsilon. On the other hand, like when we are not willing to assume smoothness, but rather we want to assume only strong convexity, then the best that we can do is actually like we do see some improvement. We're getting the improvement from order 1 over square root of k to order 1 over k, as is stated in this theorem. However, this is like a relatively smaller improvement comparing to 1 over k to e to the power of minus k. Okay, yeah, we do have a little bit of improvement, but that's not that significant, especially when m is often like a very small quantity. So so one question that I'd like you guys to think about is that what are the functions that are non-smooth but strongly convex? Okay, so I've given the answer in one of the previous questions, but I'll have you thinking about it here before I review the answer. So f is strongly convex if fx minus half m x squared is convex. Okay, yeah, to assure you that there are actually such functions that are non-smooth, non-differentiable, but strongly convex. So here's an example. Okay, so take one quadratic function, take another quadratic function. Each one is m strongly convex. So the maximum of f1x and f2x is one function that is also m strongly convex, but not differentiable, right? So this is a function, right? This is a function, right? So clearly, since either of these functions is lower bounded by this quadratic function, then the maximum of this is also lower bounded by this quadratic function. Okay. So we won't be actually proving this theorem until the second half of the course. So, but then it becomes much easier to prove this since it can be stated as a simple corollary when we do online convex optimization with a sequence of adversarially chosen convex loss functions. Okay, so what are the other improvements that are possible for non-smooth optimization problems? So since Nesterov has famously shown that we cannot do better than the 1 over epsilon square rate for the family of Lipschitz convex functions, so which means that we have to somehow change the setting a little bit and consider a family of problems that are a subset of these set of functions, but maybe those functions would admit, those optimization problems would admit a faster rate. So a specific type of this function is called a composite function. So these are also constructed by Nesterov. So that's an interesting story. So a couple of years ago, I was at a optimization workshop that gathers a lot of the optimization researchers like all over the country. And then Nesterov was there. Like he's one of these leading figure in the field of optimization that everybody look up to. So people are very excited. So it turns out that there's this entire session and everybody is talking about their research, and each one of them like refers to Nesterov, and they are extensions of some of the work that Nesterov have done in the 80s. So it's really a remarkable like how short a period of time that Nesterov have created those initial ideas, such as these Oracle lower bounds, computational analysis and acceleration, which we'll be talking about briefly towards the end of today's lecture. Each one of them generates a large body of work in optimization statistics and in machine learning literature altogether. So people actually think that this phenomenon might go a little bit beyond just optimization on its own, because the Russians like were pretty ahead of the league, like in the old days, especially in the early 90s in mathematics. A lot of the mathematics that were developed later can actually find its origin in some of the like Russian language literature in the old days. Yeah, France is another country that have that kind of feature. Okay, so let's go back to the lecture. We consider the family of problems that's called composite functions, where f decomposes to gx plus hx, where gx is a smooth function that are differentiable, where hx is a convex but possibly non-smooth function. Okay, so when is this family of problems easier to solve than the generic non-smooth function? So this happens when this h is somewhat simple. So we'll formalize it in just a little bit. So for a lot of problems when h is sufficiently simple and g is smooth, then the conclusion is that we can essentially achieve the same convergence rate of the gradient descent with a very simple algorithm that matches everything of the gradient descent. Yet we're solving a non-smooth optimization problem because h is not smooth. Okay. So examples of this include, of course, logistic L1 regularized logistic regression when this is one norm, and when this is say the logistic loss. Okay. So here's how the algorithm works. Right? So recall that in gradient descent, we are doing this quadratic approximation of the objective function f by constructing this quadratic upper bound, and by choosing t to be sufficiently small, okay, this remains an upper bound. And then we can get that the choice of t by choosing t to be 1 over L, so that the right-hand side will become bigger than 2L. And then using the first order condition, that's very much like a Taylor series of expansions, then we end up getting the fact that this is always an upper bound. So this kind of a method or principle of constructing iterative algorithm is called majorization minimization. So by constructing a quadratic upper bound that's easier to minimize, so we are majorizing the original function f of x, and then by minimizing this quadratic function, using a simple update, so we're minimizing this surrogate. So by iteratively doing that, often you can construct meaningful algorithm. And gradient descent is one example of this. So So the idea of solving the composite function is exactly the same thing. So instead of constructing the quadratic approximation of the whole thing, let's just construct the quadratic approximation of this smooth part of the function g using something called g tilde, right? So we can do the same thing and then construct a quadratic approximation of the smooth part of the object of the optimization, and then like since using the same kind of way of completing the square, we can write the argmin to be the same as the solving a quadratic optimization and plus an additional hz. So notice that what has changed. So instead of having a generic gx to minimize, now we have something that's quadratic. Quadratic in X with a covariance matrix or with a Hessian matrix being identity. So that makes it significantly easier. Okay, so so this is closely related to doing the gradient descent. So you can think about this algorithm that takes two steps. That you first move along the gradient direction. Okay, you first move along the gradient direction before you solve this kind of optimization problem that is quadratic. Okay, so notice that this x is now the input. So you first update x to xk minus half by using xk minus 1 minus tk gradient of g at xk minus 1. And then the second step, in the second step, you update xk to be a so-called prox operator. Okay, so this is a proximity operator or proximal map. It's a mapping that's defined by the argmin of what we've seen in the previous previous slide. Okay, so you do this prox map with a parameter with a parameter t. And taking the input of simply xk minus half. Okay, so so actually, like we can also rewrite this update into something that's more similar to gradient descent. So suppose we define this so-called generalized gradient or Nesterov gradient map this way. Then by the simple algebra, then we can rewrite the update rule of this following 1 and 2 into a single update that moves xk towards a negative generalized gradient direction. Okay, so we'll have more insight about this in the next lecture when we talk about multiple different interpretation of the proximal gradient methods. Okay, so why are we doing this? So it looks like we're simply like changing the more difficult optimization problem of minimizing g plus h with something that seems slightly simpler, right, in every iteration. But then we have to solve one optimization problem in every iteration. So solving this prox, so solving the second step is an optimization problem in its own right. Although it's quadratic, but it is still having the composite form with this smooth term and non-smooth term. We still haven't addressed the non-smooth term at all. So it turns out that there are many cases where this proximal mapping can be evaluated very efficiently, and sometimes it's just linear in the number of parameters that you're optimizing over. So often they can be even evaluated analytically. So we know the closed form solution of that. So we don't have to use the iterative algorithm to solve that. And if the prox is actually efficient and every iteration of the previous algorithm, the proximal gradient descent algorithm, becomes efficient. And in terms of the convergence, we can essentially get exactly the same guarantee of the gradient descent that depends only on the smoothness of the smooth part of the composite objective function. Okay. So you get to prove the convergence of the proximal gradient descent in homework 2, and then make use of the generalized gradient argument. You will see that it will be almost identical to after you do the gradient map. The convergence proof will be almost identical to that of the gradient descent, in the sense that you first establish the descent lemma, and then you apply the convexity to construct a particular telescoping sum. And there are gonna be many subproblems that guides you towards discovering this interesting proof that generalizes the gradient descent convergence to proximal gradient methods. Okay, so let's give an example of when this optimization is actually easier to do. When is this proximal operator something easy to solve comparing to solving the original problems of the same structure? Okay, so let's revisit the same old example of lasso. So you have a smooth part that is just a linear regression objective, and you have a non-smooth part that's given to you by lambda, the regularization parameter plus the sum of the absolute value of the coefficients. Okay, so the proximal mapping that comes as the second step of the proximal gradient algorithm tries to solve a problem of this form. Okay, so even though the lasso is more difficult to solve, so we've worked out this optimality guarantee in the previous lecture from the subgradient optimality guarantee, but like we cannot really read off a closed form solution from there. But there was this special case where we worked out carefully when this X is an identity matrix, where the solution is actually easy. So that boils down to the so-called soft thresholding operator, where you're shrinking you're shrinking everything by, so you guys still remember this picture? When your input beta is here, then you're shrinking it by parameter lambda. If you're larger than lambda, you're adding minus lambda to it. If you are smaller than minus lambda, if you are within the minus lambda and lambda zone, then the output will be everything to shrinking to 0. So that's something that you can actually do coordinate-wise by just simply post-processing every update, every gradient update that consider only the smooth part of the objective. Okay, so if we compare the subgradient method and the proximal gradient descent for this for the lasso problem, okay, so this algorithm is also called iterative soft thresholding algorithm, like ISTA. That's coming from a very popular paper more than 10 years ago. So if you compare the convergence of the two, the subgradient method and then the proximal gradient method, you see that even although they are both like sublinear convergence, but the proximal gradient is significantly faster than that of the subgradient method. So another benefit of doing proximal gradient instead of the subgradient is that it allows us to choose a learning rate using the same old idea of backtracking line search. Okay, so so we can basically do the following. We can consider only the smooth part of the objective function and then choose initial learning rate that's somewhat large. And if this sufficient descent condition is not satisfied, sufficient descent. If this sufficient descent condition is not satisfied, then you make t smaller by a factor of beta. You make it two times smaller, for example, and that happens to be an adaptive choice of learning rates that do not require any additional tuning parameters for this algorithm to work. And all you have to do is to evaluate this this generalized gradient, like once and then move it towards the different directions for multiple times, and you suffer a little bit more cost of evaluating the objective functions, but now you have something that's fully adaptive. So there are alternative ways of doing this, doing line search, but the point really is that like the algorithm will be more practical because it doesn't require experts to set this learning rate very delicately. So, so this is a theorem that you're going to be proving for the homework. So so we can see that as long as we choose the learning rate to be smaller than 1 over L, so this is the same old learning rate from the gradient descent, then we get the same order 1 over K convergence like the gradient, like that of the gradient descent. So let's consider another example of this. So previously we talked about lasso. So now let's talk about an example that works with matrices. Okay, say Yij are the input. So a motivation of matrix completion problems are is the recommendation system. So movie recommendation, and this matrix Y are the observed ratings of individuals on different movies, user I on movie J, and this omega, so this is a mask saying that these are all the observations that we have. And the question of matrix completion is that can we use the data to infer those movies that you haven't seen, and can we make valid predictions of what's your opinion on Fight Club, like given that you have seen like other movies of Brad Pitt and liked it a lot. So this is an ill-posed problem. That's why people usually want to find solutions, find solutions B that satisfy conditions that a B is low rank. But rank constraints or rank regularization is non-convex, so we can relax it into the trace norm or the nuclear norm of this matrix. Okay, that gives rise to a convex optimization problem. You can clearly reformulate this as a semi-definite program since this works with eigenvalues. But that's like a very inefficient way of doing that. And can we use the techniques that we learned today to design a better algorithm to solve this problem? So again, like remember that the trace norm is simply the sum of the singular values of a matrix B. Okay. So it turns out that this falls into the structure of the composite optimization problem, where this term is smooth and this term is non-smooth. So we can actually apply proximal gradient methods to this problem. Okay, so when we do that, the gradient is easy to calculate since this is quadratic. So it involves like taking the difference and then put everything that you do not observe to be 0 and everything else being 0. And then that's a matrix gradient. And then the prox operator looks like the following shape. So you'd like to minimize a quadratic function plus the trace norm regularization. So the thing that we can do is that we can diagonalize this matrix by taking the singular value decomposition. And that suddenly allows us to solve the prox operator very much like the idea of soft thresholding. So instead of thresholding on each coordinate, now we are thresholding on the singular values of this matrix B at level L. So this involves like decreasing the every individual singular value of the matrix B by a fixed extent lambda. If we hit 0, then we stop at 0. So that's called the matrix soft thresholding or matrix shrinkage shrinkage operator. So with that shrinkage operator, this is relatively easy to implement. You can simply solve this by running a singular value decomposition and then shrink its singular values and then reconstruct the matrix by multiplying everything back. Okay, so I'll leave this proof to you, like for your own readings. But basically, this involves like taking the singular value decomposition and then like applying the first order optimality condition by the subgradients. And now that we know what the subdifferential of the trace norm is, we can make use of it to construct this closed form solution called matrix soft-threshold. Okay, so I'll leave this as an exercise for you to work out yourself. Okay, so the final proximal gradient update steps for solving the matrix completion problems would be to first move towards a gradient direction a little bit, and then solve SVD, shrink the singular values, and then reconstruct the matrix. So that gives us update. So this iterative approach, like when it was first proposed, it's called soft impute algorithm, in contrast to the hard impute algorithm that replaces the soft thresholding with a hard thresholding that projects things to say exactly rank to satisfy an exact rank constraint, or projected to get rid of everything that has singular values larger than lambda. So that's the corresponding hard impute algorithm. But this algorithm called soft impute is essentially just a proximal gradient algorithm, and the convergence guarantees of proximal gradient algorithm applies here. That gives us a meaningful meaningful computational analysis for this algorithm. Okay, so so the proximal gradient descent is also like a very general object when we substitute this h to be h and g to be specific quantities, and so we get a specialized version of this algorithm that are known by other names. So when we choose h to be 0, so obviously we recover the gradient descent. And when we choose the h to be the indicator function to a convex set, and then this suddenly becomes a projected gradient descent. So notice that we talk about the projected subgradient methods and have a 1 over square root of k convergence. What this is saying is that when the g part is actually differentiable, then you can come up with, you can invoke the proximal gradients convergence rate, and then show the much faster 1 over k convergence of the projected gradient method. When g is equal to 0 and h is a only function that you want to minimize, so this happens to be something called the proximal point algorithm that predates the proximal gradient methods. So notice that this g equals to 0 is perfectly smooth because the gradient of it is 0 everywhere. So the smoothness constant is actually 0, is as small as it gets. So all these algorithms turns out to have the same order 1 over epsilon convergence rate. And we can recover that from the theorem that you're going to be proving in homework 2. Okay, so so specifically in projected gradient descent, just to convince you, with this indicator function written here, then the proximal operator would simply be looking like this. So you want to minimize a quadratic function with an input x over z, plus an indicator function. And notice that this is infinity. So the only solution here would be the solution that's inside a convex set, right? So and that's closest to your input x. Okay, so what is that? By definition, this is a projection operator. So in other words, the prox of x is simply when h is an indicator function, is a projection of the input x to this convex set C. Okay, so to visualize that a little bit, suppose the red region here, this L1 norm is your constraint set. Okay, so maybe you are minimizing y minus a transpose x plus I guess plus an indicator subject to x 1 smaller than say lambda. So this will be the this will be the constraint set, and the contours will be the equipotential contour of this quadratic function. So suppose you are here, they are moving towards a gradient direction that's perpendicular to this equipotential line. That's this direction. And you move a little bit, that moves you outside the feasible region. And what the projected gradient descent would do is to project it back to the closest point within the convex set. Okay. The proximal point algorithm will be keep solving this kind of iterations. So this is an algorithm that's different from proximal from the subgradient methods that can be used to solve H. But suppose you can solve the proximal gradient updates. Suppose you can solve the prox operator faster than suppose you can solve like or maybe just as fast as a gradient update, just as quickly as constructing a particular subgradient direction, then this will be a more effective algorithm. So it really depends on how much computation you need to spend within every iteration. Okay, so I guess I will stop here, and then we'll continue to talk about proximal gradient methods in the next lecture. And also I'll be talking about accelerated version of the gradient descent method and the proximal gradient methods in the next lecture. All right, so so I'll go over the remaining slides in the current lecture, and then I'll make a start and hopefully finish the next lecture on the interpretation of the proximal gradient methods and with a little bit more mathematics and from the operator point of view in the next lecture. So let me fast forward to the list of readings. Okay, so these are so these are some of the Nesferov's lecture notes and Stephen Boyd's lecture notes for EE264B, and Polia's original analysis on first order methods have a significant impact on some of the things that's being developed here, and Vandenberg's lecture notes are also referred to in the construction of this lecture. All right, yeah, thank you very much. I'll spend the next 5 minutes to, I guess, address any questions that you may have. If not, a lot of the questions in homework 2 are already ready, so we've covered sufficient material so you can already start working on homework 2. Yeah, it's definitely not all of them, but a lot of questions are already covered.
Thank you.
Yeah, thank you.